Hey folks, this is the third and final lesson in the nuclear chemistry unit. In this lesson we're going to be talking about half-life. So our two main goals for this lesson: first, define what half-life means and what it tells us about how each of our various radioactive isotopes will decay. And then we're going to spend a lot of our time just practicing solving half-life problems, which will allow us to predict one of two things primarily. Number one, the amount of substance that's going to remain after some period of time has passed, or figure out how old a substance is based on how much of that substance still remains. Now, before we launch into half-life, first we've got to have a little bit more math under our belt. Now, this ln that you see here stands for natural log, so it's much like the logarithms that we dealt with in our acids and bases unit. Hopefully you've seen them at some point in your math classes, but you should have on your calculator an ln button that stands for natural log. So let's start with letter A, trying to figure out the natural log of a known number. Now, to solve this, all you have to do on your calculator is punch in ln and then the number you're trying to find the natural log of. So if you try that, you should come up with 1.240. Now, the other type of problem that you could encounter would be like B, where we're trying to find the natural log of an unknown variable. So in order to solve for x by itself, we can't divide both sides by natural log. It just doesn't work. For us to undo that natural log and get x by itself on one side, what we have to do is use e. Now, e should show up somewhere on your calculator, probably near the natural log. So in order to undo this natural log and solve for x by itself, what we're going to do is take everything on the other side and make that the exponent on e. Okay? So in other words, then, x is just equal to e to the negative 2.57 power. When we plug that into our calculator, we get 7.65 times 10 to the negative 2, or 0.0765. So that's the last new mathematical tool we need to have in order to solve these half-life problems. Now, half-life just describes the amount of time it's going to take for half of our sample to decay into something else, to transmutate into a different isotope, which means that for every half-life that goes by, we're going to expect half of the amount of substance that we have to decay and only half of it to remain. So if we look at this graph to help us out, here we're seeing on the y-axis the mass of our substance, in this case oxygen 15, and on the x-axis we have time. So we see that we're starting out with 20 milligrams of our oxygen. After one half-life has passed, we're down to 10, because 10 is half of 20. After another half-life goes by, we have it again, so it goes from 10 down to 5 milligrams. And then after the third half-life, which answers the first part of this question, we're going to divide in half again, which brings us down to 2.5 milligrams. From there, we could continue to divide in half for every half-life that goes by, which means that after the fourth half-life, we'd be down to 1.25, and by the fifth half-life, we would be down to 0.625 milligrams. So for every half-life that goes by, we just divide in half again. That's all there is to it. Now, different isotopes are going to have vastly different half-lives, which means that it takes very different amounts of time for them to decay. Now, as you may remember when we were talking about different types of nuclear decay, sometimes an isotope will have to go through multiple iterations of nuclear decay before it becomes stable. So for example, we see the chain of decay needed to make radium-226 into a stable isotope, in this case, lead-206. Now, based on this picture, you would think that all of them are just happening boom, 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 one right after the other. However, we can see that these different links in the chain will take different amounts of time based on the half-life of each of those substances that it becomes along the way. So our radon-226, for example, our very first substance that we start out as, has a half-life of 1,600 years. So it's going to take a long time for us to see a significant amount of our radium turning into radon, which is the second thing we have here. But radon has a half-life of only 3.82 days. So this link is going to go really quickly, whereas this link is going to take a really long time. Okay? So basically all this is telling us then is that different isotopes are going to have different half-lives, which means that they're occurring over different time frames. Okay. Now, for another example for you, radium-234 has a half-life of 3.82 days. If we start with 50 grams, how much do we expect to be left after 3.82 days? Well, 3.82 days is just one half-life, so we're just going to divide our starting amount of 50 in half once to become 25 grams. Now, after 7.64 days, that may sound like a weird number, but all we have to do is realize 7.64 days is just 2 half-lives. So that means we just divide in half again for 12.5 grams. 11.46 days, as you can see, is 3 half-lives. So we divide in half again. And 15.28 days, I think you see where this pattern is going. It's 4 half-lives, so we divide in half again. Now this is nice and easy because the amount of time that we keep checking after is always a multiple of the half-life. But I could, in fact, ask you how much would be left after 10.2 days, which is not an exact multiple of our half-life. Or I could ask you how long it's going to take before we end up with 30.8 grams, which is not half or a quarter or an eighth of our starting amount. So this method of just dividing in half for each half-life is useful sometimes, but sometimes we get icky numbers, and for those we're going to need some formulas, which we're going to get to in just a moment. Before we do that, just one more thing for you to consider. We've got uranium-238 here. Now on the left you see the long decay chain of uranium. Don't worry too much about that. But basically what we see is that the half-life, represented by T with a little 1/2 half-life, of uranium-238 is 4.51 times 10 to the 9th years, 4.5 billion years. The question here is how many years is it going to take for 100 atoms of uranium-238 to decay down to just 25 atoms of uranium-238 and then 75 atoms of, other things, in this case, lead. Now, in order to figure this out, one thing that we could do is make a table, okay? Looking at the number of atoms that we have versus the number of years that have gone by, okay? So at the very beginning, times 0, we've got 100 atoms. Now, how long is it going to take for us to have 50 atoms is 1 half-life, 4.51 times 10 to the 9th years, because that's the amount of time it takes for it to divide in half. Now, if our ultimate goal is to get to 25 atoms, that means we need to divide in half again. That means we need another half-life to go by, which is 9.02 times 10 to the 9th years. So we know that then it's going to take 2 half-lives, or 9 billion years, for our 100 atoms of uranium-238 to decay down to just 25 atoms of uranium-238. Now, as I mentioned, we're sometimes going to get into slightly ickier problems where we can't just do it by dividing in half a certain number of times. And for that, we need 2 formulas. And they are these. So we've got these 2 formulas that are usually going to be used in conjunction with each other. Chances are good for any given problem, you're going to need to use both of these. And we'll explain how to do that. To walk you through each of these variables, in this first equation we've got N with a little t. That stands for the number of atoms, or the mass, of our substance after our time has gone by. So this is sort of like our ending amount right here. Now this N0 represents our starting amount, so that could be starting number of atoms or starting mass of our substance. K is the next thing, and K tends to be very useful because it's the one variable that shows up in both of these problems. So frequently you'll solve for K in one of these and then plug it into the other equation. K stands for the decay constant of that particular isotope. It's going to be different for every substance, and it kind of tells us something about the time frame over which that particular substance decays. Okay. T here, just regular T, not T with the little 1/2, just regular T, represents the amount of time that goes by between our starting amount and our ending amount. This is the amount of time that's gone by. This T with a little 1/2 represents the half-life of the substance, how long it takes for half of the substance to decay. So now we're just going to try a few different examples of this. Okay. So first one, we've got 2,259 atoms of uranium-238. We know we started with 2,560. We want to figure out how old the sample is. Right? So again, we've got a couple of equations to help us out. We're going to start with that natural log one. Let's fill in everything that we know. Okay. So we know that our ending amount is 2,259 atoms. We know that our starting amount was 2,560 atoms. We don't currently know K or T. But we can solve for K using that second equation, where the half-life is equal to 0.693 over K. We know the half-life because it was given to us in the previous problem. The half-life of uranium-238 is 4.51 times 10 to the 9 years. So I'm going to plug that into that second equation so that I can solve for K. And when I do that, K happens to be equal to 1.53659 times 10 to the negative 10. And so now that I have that, I can go and plug that back into that first equation for K there. And now I just have to do a little bit of algebra to solve for T. So I'm going to solve for the natural log of 2,259 using my calculator, and then subtract from that the natural log of 2,560. And when I do that, I get negative 0.1250850, and that's equal to negative K times T. I'm going to divide both sides by negative K. And I determined then that T, the amount of time that's passed between my starting amount of uranium-238 and now, is 8.122 times 10 to the 8th years, 812 million years. Another problem. We've got a watch that was made in 1521. At the time that it was created, 24.5 milligrams of radium-226 were put into it. I don't know why, they just felt like it, I guess. But then we pick up this watch again in 1967 and discover that at that point there's only 20.2 milligrams of radium-226. Now what we're trying to do is, from this information, we can determine the half-life of radium-226. So again, let's plug in everything that we know. We know our ending amount of radium-226 is 20.2 milligrams. We know that our starting amount was 24.5. And we know the number of years that have gone by just subtracting the two dates from each other, 1967 minus 1521. So we determined that this watch is 446 years old. Now from that information, I can do a little algebra and discover that K then, the decay constant, is 4.327 times 10 to the negative 4. And then I can plug that into my second equation to solve for the half-life. So when I plug that in as my value for K, I determined that the half-life of radium-226 is 1,600 years, which is just what I said it was a few slides ago, so, you know, good. All right, third sample problem for us to look at. We've got a sample of wood, and we know that it has only 32% of the carbon-14 that it had when it first came into existence. We want to figure out how old this wood is. Now, by the way, this is how carbon dating works, how we're able to figure out the age of really old fossils, is we can look at the amount of carbon-14 in it and compare that to the amount of carbon-14 that should be in a brand new substance, and then from that we can figure out how old it is. Okay. So again, I'm going to start filling in the things that I know. What's tricky about this is I don't know my ending amount of carbon-14, nor do I know my starting amount of carbon-14. But here's what's useful. All that really matters is that I have the correct relationship between the ending and starting amount. All that really matters is that my NT value is 32% of my N0 value. It doesn't really matter what those numbers are. So in fact, I could choose any number I want for N0, and as long as I just make NT equal to 32% of that N0 value, I'm fine. So I can choose whatever I want. I'm going to choose a nice easy number like 100. So I'll assume that I started with 100 grams of carbon-14. That would mean that now I would have to have 32 grams of carbon-14. Totally fair to do. So anytime we run into a percentage problem like this, we can just make up the numbers as long as the relationship between those two numbers is the same as was described in the original problem. Okay. So I've plugged in some numbers for my ending and my starting amounts. Once again, in order to solve for the age of the sample, I'm going to need to know K. And I can solve for K using that second equation by plugging in the half-life of 5,760 years. So when I do that, I solve for K, and I determine that it's 1.21 times 10 to the negative 4, so I can just plug that into my first equation. Okay. Do a little bit of plugging in on my calculator, subtracting natural log of 100 from natural log of 32, and then divide both sides, and I determine that this sample of wood is 9,400 years old. Pretty nifty. Last sample problem to go through. Okay. I know that the half-life of iodine-123 is 13 hours. I want to figure out if I started out with 64 grams of iodine-123, how much will remain after 31 hours. Okay. So I'm solving for my ending amount, NT. So here's what I'm going to do. I'm going to start by solving for K, because I always seem to need to do that, so let's just get it out of the way now. I know the half-life is 13 hours, so I'll plug that in for my half-life, and determine that K is 5.33076 times 10 to the negative 2. And I can now plug that back into my first equation, the natural log equation. So here's everything I know. I know my starting amount was 64, I know K because of the half-life, and I know that the time that's passed is 31 hours. So now I'm just going to plug those values into my calculator until I determine that the natural log of my ending amount is 2.5 blah 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 blah. Now you cannot stop there. I have to solve for NT. And in order to do that, I'm going to have to undo that natural log, which, if you recall from the very beginning of this lesson, we can do using that funny number E. So the E will undo the natural log, and then all I need to do to solve for my ending amount of my iodine-123 is just do E to the power of 2.506347, which is 12.3. And I know that my units on that is grams because my starting number of 64 was also in grams. So I'm going to end up in grams as well. That is all, folks. I hope you have a wonderful day.